good afternoon, everybody. I want to thank the QCware for inviting us to make this presentation. I'm going to talk a little bit about quantum advantage and what it means and when you might expect it. But before I do that, let me just introduce both myself and our company. GQI, Global Quantum Intelligence, is a new company. We were formed as a merger about 6 months ago from 3 different market analysts. I ran the Quantum Computing Report. You may be familiar with that website. There's the Fact-Based Insight, which was in London, and Interference Advisors. So we have vast experience in the quantum and electronics industries. I actually started the Quantum Computing Report in 2015. And we have a lot of experience in the computer field in general. We do a lot of consulting, we do a lot of work, we write reports, and these are some of the companies we've worked with in the past. We are the only company that's solely focused on quantum. We don't write reports on blockchain or artificial intelligence, that type of thing. We're solely in quantum. So we're very focused, and we really specialize in this area. So let me start with some definitions. One of the issues we have in the quantum industry is that people do not use the same terminology. It differs. Let me start with the definitions that I will use for this presentation just to make things clear. There's a concept called quantum supremacy, which was introduced in 2017, actually in Q2B23, by Professor John Preskill at Caltech. Actually, it was before that, I'm sorry, at Caltech. And that is just a demonstration of how a quantum processor can execute a problem that is beyond a classical computer. But in his definition, it did not have to be a useful problem. And in fact, some of the things I'll just show in the next slide are artificial problems, just to demonstrate that you could do it. I use the term quantum advantage for something where you are demonstrating a useful application that could be used to make money or to help you with scientific research. Now, a lot of people think that you can only use quantum advantage when it's completely impossible or intractable in a classical computer. But actually, you can have an advantage if it's lower in cost, or if it's more accurate, or just plain faster. And there's been a lot of money, and by the way, people use different terms. Some people call quantum advantage quantum value. Some people call it quantum utility. But at the end of the day, there's been a lot of money invested in quantum already, and there will continue to be a lot of investments, both from government and VCs. They're interested in seeing quantum advantage. They don't want to, venture capitalist doesn't want to invest money to get a whole bunch of papers put out there. They want people to make money. So those are the terms I will use for the rest of this presentation. So there have been a number of notable quantum supremacy experiments. The first one was done in 2019 by Google. It was a very famous 53 qubits. And then several groups in China came up with their own experiments. There was a photonic-based experiment. There was a replication, essentially, of what Google did with 60 qubits instead of 53 qubits. Google, of course, just a few months ago, upped that up to 70 qubits. And the most recent one, actually was talked about earlier this morning, the IBM keynote, was a paper that published in Nature, where they called it quantum utility, which is, I would call, a 100 qubit by 60 level experiment where they really showed the power of some of the quantum quantum error suppression algorithms that they were using. One notable thing about all these experiments, though, is that after the papers came out, Classical people came out and said, no, 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 we have a better way of doing it classically. That's specific to, this is actually the most recent example. Just last month, IBM came out with that paper on June 14th, and within 2 weeks, 3 different groups started saying, hey, we can do something similar with classical. So you should never count out classical computing. It's achieving quantum advantage is going to be a real, is a challenge. People will overcome that challenge, but it's not easy. And part of the reason for that is that classical computers are still continuing to increase at a very fast pace. You hear these presentations where people say, Moore's law is running out of gas, that it's slowing down and we have to move to quantum or else we won't continue improving classical computing. But what they're forgetting is that the classical computer scientists, number one, are very innovative, and they're doing a whole bunch of things. They're moving to different architectures, things like GPUs, non-von Neumann type of architectures. They're coming up with smarter algorithms. They are building larger and larger data centers. And semiconductors are still improving too, but perhaps not at the same pace it was 20 years ago. And what I have here on the graph is an organization that shows the performance of the top 500 supercomputers in the world. Number 2, by the way, is Fugaku, which is at Riken University. But if you look at the graph, the red line is the top one, is number 1 on the list. The yellow line is number 500 on the list. But all of these are doing millions and hundreds of millions of petaflops. And it's not really decreasing. It's continuing to increase at a faster rate. So quantum advantage is a moving target. You may have a level here, and you say classical's here, but then classical's going to go up. So the quantum people are going to have to continue to improve the performance of their machines. One of the things that we're seeing, and this is perhaps a more recent phenomena, is that more and more software companies are talking about quantum inspired. Even QCware just came out with a product called, was it Prometheus, that does quantum chemistry in a quantum inspired. We had several people talking about this morning about using quantum inspired. And this is part of the reaction to the fact that classical is still getting better and better. Now, a lot of those implementations where people are doing quantum inspired, perhaps they're using an algorithm like a tensor network-based algorithm and running on GPUs, which are well suited to that. One of the advantages of that particular approach is the fact that as the quantum computers get higher and higher in performance, then at some point the quantum computers will surpass even the largest GPU systems, and some of those algorithms you'll be able to easily convert to run on the quantum computers. But we are seeing that in the industry today. So quantum inspired is not quantum. It doesn't use quantum physics. It doesn't use superposition. But it's very innovative classical, and you should definitely not count it out. So we still believe at GQI that quantum computer will be very valuable and will definitely win. We plot the performance increases year after year. Sometimes it's month after month. And the industry over the past 5 years has just done an amazing job of continuing to improve the number of qubits, the quality level of the qubits, even the performance level of the qubits. So we do believe that over the next several years, and I'll be more specific on my last slide, that quantum for certain applications will be able to beat out classical. What the graph here shows is actually something, we give credit to IBM on this, and this is IBM's view, which we agree with. The quantum industry is going through sort of a transition right now. The stage we're in is called NISC, Near-Term Intermediate Scale, which means it does not use error correction codes. You can use error suppression techniques, like what Q Control talked about yesterday. You can use error mitigation, and that will improve things, but it will not reduce the error level to zero. Now, there are some algorithms where NISC will never work. For example, there's Shor's algorithm for factoring a 2048-bit code. NISC will never be good enough to make that happen. From that, and there's many more types of applications, you're gonna need fault tolerance. But there will be some range, and again, next few years, where the NISC will actually be the best solution for some applications. In this chart here, lower is better. So it's essentially the relative execution time or the execution cost. And that area where it says classical wins, classical is the best choice. You will move into an area where the NISC wins. And then later on, you'll move into the area where fault tolerance is the right approach. And a lot of that has to do with the complexity of the part, complexity of the problem. You know, the number of nodes, for example, in a graph or something like that, or the number of bits if you're trying to do a factor. So, but these curves are shifting, and they'll change, of course. The shapes of the curve will change depending on the specific problem you're working on. As the hardware gets faster, the curves will actually move down. And as the algorithms get better, and people are getting more innovative algorithms, those curves will tend to flatten a little bit. So, so we do a lot of talking. We go to many of these conferences. We talk on a daily basis with many of the key players in the quantum industry. And one question I ask them is, to achieve quantum advantage, to be able to do something that's useful, that you can make money with, will you need a error-corrected machine? And the opinions I get back, I would say about 50% of the people say, yes, you're absolutely going to need an error-corrected machine, and about 50% of the people say no. And I have a couple of the key players. If you talk with a company like Intel or PsiQuantum, they're saying, look, you're going to need error correction. That's the only way you'll ever be able to do something useful. If you talk with IBM or even listen to the IBM presentation this morning, they talk about quantum utility and Pascal also. You just go to their booth. They'll say, we think that you'll be able to do that. You'll be able to do something without error correction. So the reason to talk about the people who say they can do something with NISC, and the reasons they give us is, number one, they're using heavy use of hybrid, classical and quantum processors working together, algorithms like QAOA, quantum approximation optimization algorithm, VQE, variable quantum eigensolvers, which are using architecture where you're cycling the data back and forth between the classical computer and the quantum computer. Another thing is relatively new is this thing called analog modes. There are two companies, neutral atom companies, Pascal and Quera, which are doing analog processing, and they say they say, quite frankly, we'll be able to achieve quantum advantage before people doing the classical gate-based, and it could be in the near future. Hardware is getting better. We're constantly seeing people do better things with the qubit fidelities. That's probably the key thing right now that's holding back quantum advantage, is that the qubits just are not good enough for most applications to be able to give you an answer that makes sense, particularly after you run it through, hundreds or thousands or millions of gates. You'll just get random numbers out of the end because the qubits are not good enough, as well as some of the error suppression, error mitigation techniques we've talked about. So there's a lot of work there to achieve this quantum value. So at GQI, we look at this in detail. We have several reports which will go through this in detail, and I'll just touch upon it, just have a few minutes remaining. We believe that you need to make improvements at all levels of the stack. This here is our hardware stack. At the very top is what I call the applications and the user community. You have the framework and the architectures. You have the control plane, the control logic, the quantum plane, and the chips themselves. And you're going to need to make improvements in all those areas. And to go through it in just a little bit more detail in the time remaining, I'm going to start at the very top of the stack, which is the applications. You will need, at least initially, when we're still in this NISQ period, you're going to need to choose your applications carefully. You'll never be able to run Shor's algorithm, for example, on a NISQ computer. But there are some, we think, perhaps in the optimization area or in the generative AI area where you might be able to do that. So you have to pick it carefully. And then you have to figure out the right algorithms. So some algorithms are more efficient than others. You want to, if you do write a quantum program, one of the tricks is to figure out how to reduce the number of levels that it goes through. Because every time it goes through a new level, that's a new potential source of error, as well as the various frameworks that you're using, the software, how well it optimizes it. One thing we're watching very carefully is, again, it was mentioned this morning by IBM, is a 100 by 100 challenge. And what that means is 100 qubits through 100 levels, and be able to get a good answer at the end. No one can do that right now, at least in the digital world, with gate-based computers. So there's a bunch of things. I'm not going to go into a lot of the details that are shown on that slide. You'll be able to look at it later, and we can explain in some of our reports. But there's a lot of things that need to happen. And then moving down, this gets more into the hardware and the architecture layers. Things like choosing the connectivity of your hardware, being able to use the right algorithms to control them, sending the right control pulses to the thing. Even material selection. For example, using what's called Si-28, which is the 28 isotope, a special isotope of silicon. All that type of stuff, and the layout of the chips, all that stuff needs to happen. So really to summarize, and the bottom line is this is what we believe. If the venture capitalists ask us, okay, when are we going to see quantum advantage? Our belief is that there will be a handful of applications in the NISQ era that will be able to do that, and we'll be able to see quantum advantage in the next 2 to 3 years. We see enough improvements that will happen. But the majority of the applications that we see, that people talk about in quantum, will really need to wait for fault-tolerant computers. But I tell people that you should never underestimate the innovativeness of the quantum scientists. They come up with very clever things, and even though something may look impossible, they'll be able to figure out a way around it. So bottom line, you'll see a few applications in the next 2 to 3 years with NISC level computers, but the inflection point when you're really going to get a very large number of applications that are showing quantum advantage will require the fully fault-tolerant computers, and that's still 5 to 10 years away. So with that, I think I'm out of time, but so, okay, thank you.